Hello everyone, I am Ananya Bora. This project is the Inventory Expiry Management System. It stores the products and their batches, sells stock by earliest expiry, and removes the expired batches automatically. I will explain the problem statement, the data structures chosen, and Shloka will show the implementation live, and Mahima will present the results. Problem definition. Shops need to avoid waste by selling items that expire sooner first. Manual checking is slow and error prone. This system supports five functions: add and search products by ID, add batches with quantities and expiry dates, sell units following expiry order, remove expired batches using today's date, and display the full inventory. Dates are stored in YYYY-MM-DD so we can compare them easily. The system must be correct, efficient, and memory safe. We use binary search tree for products and a per product queue of batches. Product IDs are unique and mixed up, so BST lets us insert and find products in about log n time on average. Instead of scanning every product, each product has a linked list queue of batches kept in ascending expiry order. That makes selling constant time at the head because the earliest expiry batch stays at the front. Adding a new batch takes time proportional to the number of batches for that product since we insert in sorted order. This combination balances fast product lookup and correct FIFO expiry handling. This is the visual where product where it shows how the products will be stored in a binary search tree and per product queue of batches.
I'll show the implementation details by sharing my code blocks view. So here we can see the code for the project. It's written in C. First, we import the necessary libraries that we require. Now here we can see there are three structures created. One is for which represents a product in the BST. This one represents the queue of batches of every product. And this is every batch in that queue of batches. This function make product node initializes a product, the struct product that we have created, and make batch node initializes a batch in the queue of batches. Add new product node function. This adds a new product to the binary search tree based on its ID. Find given product node will search for a given product based on its ID. Add batch to batch queue. So every product will hold a queue of batches. So we want to add a batch to that queue of batches. We can use this function. In this function, if we add an expiry date, which is coming earlier than the expiry date of the batch at the front of the queue, the system is designed such that automatically that batch with the earlier expiry date will now become the new head of the queue of batches. Remove batch from queue front. This function removes a particular batch from the front of the queue to ensure FIFO selling of batches based on their expiry dates. Add batch for a given product will just add a batch in the queue of batches according to the expiry date. Sell given units of product. So selling this function simulates selling in the inventory management system. It will also print appropriate messages if there isn't enough stock available, and also cross batch selling is possible. This is the most important function, that is removing expired product batches, where we use strcmp to compare a particular batch expiry date with the current date that will be entered by the user. And if this current batch is expired, then it will be removed from the inventory. This function shows the total product inventory. In this function and in showing the total inventory, we use in-order traversal method. That is a recursive method of in-order traversal based on the product ID. These functions are just to free up all the memory that is occupied to prevent any leaks. Here is our main program. This is a menu-driven program. So the user will enter a choice, and on that basis, accordingly, functions will be performed, like adding a new product to the inventory, adding a new batch to the product, selling some units, removing expired batches based on the entered date, and showing the total inventory. And we can even exit by freeing up all the memory. So this is how the code implementation is. Now, we can go to the test case that we consider. I'll show this test case through the terminal. Let's consider the given test case that we have taken. We will start by adding a product. The product is milk. Then we add another product, which is butter. And we add cheese. So all these products are added. Now we'll add batches to every product. So say suppose I want to add a batch to milk. We add a batch of 20, and the expiry date that we enter is say 20th October. Now we add another batch to milk of 25 units, and the expiry date over here is 18. So over here, even though this expiry date is before 20th, the system will efficiently manage that. We'll see soon. Let's add another batch to milk of 22nd October. So if we view the inventory, we can see even though the 18th October expiry date batch was entered later by the user, the system ensured that the batch with the earliest expiry date will be kept at the front, so that selling can be done according to the expiry dates, which is essentially what we need. Let's add batches to other products as well. To butter, we add a batch of expiry date 20th and another batch to butter of expiry date 21st. And let's add a batch to cheese of 15 units, and expiry date is 22nd. Now, if we view the total inventory, we can see that how neatly it prints out all the products, its IDs, and every batch it contains. And those batches are maintained according to their expiry date. Now let's simulate selling. So we sell units of milk. I'm sorry, this one is cheese. So let's first sell cheese. And if I sell 20 units, it's going to print that 15 units could be sold, but 5 could not. So it handles that by printing user-friendly messages. Now let's add milk. Sell milk. So if I sell 40, that this is cross batch selling. 25 units could be sold from the first batch and 15 from the next. If we view the inventory, we can see that the first batch has been completely removed, and the next batch has 5 remaining. Now let's see removing expired. So that's, if today's date is considered to be 21st October, then we'll see that a batch from butter has to be removed, which has been removed over here, and a batch from milk has to be removed, which has been removed. So let's view the inventory and confirm. So we can see that butter has only one batch and milk has another, which are not expired as of now. So let's try again. And if today's date is 22nd October, we can see butter's batch is also removed, and only batch remaining finally is that of milk, which hasn't been expired yet. And finally, we can exit the system.
Let's look at the final result in detail. Initially, we had butter with 2 batches, 10 and 50 units, and milk with batches of 25, 20 and 25 units, and cheese with a 50 units. During our execution, we sold 40 units of milk and 50 units of cheese. Total 55 units sold. When expiry batches were removed, the system cleared a butter of 10 and 50 units and also removed 5 units of expired milk. A total 30 expired units removed. After all removal, only one milk batch with 25 units remain. Performance-wise, product operation use BST given O0 and average cost, and selling is constant time per batches removal since we decay at the head. Adding batches is linear in per product batches because we maintain sorted order. The system update inventory immediately after each operations and free the memory unneeded. Overall, all the correctness and efficiency goals were met for this assignment. I confirm that the code submitted is original and have attached the pregnant report screenshot which show a 7% similarity with online and parallel submission. Reference included Rima Thatrera Tata structure textbook and several open sources and GitHub project for features and ideas, and the official C language documentation for syntax and memory functions. Thank you for listening our PPT. If you have any question, go ahead.
Okay, so for storing batches, why did you prefer a queue structure instead of a stack or a simple list?
We chose a queue because it follows the FIFO principle, that is first in, first out, which directly matches how expiry-based selling works. So the oldest batch which expires first is always at the front of the queue. So selling will simply mean we dequeue from the front. A stack would also work, but it will work in the opposite way. It would always sell the newest batch first, which would be wrong. And a simple list would allow this too. But we'd constantly need to sort the list or scan through the list to find the earliest expiry, which would make it less efficient. So a queue would give both correct order as well as efficient constant time operations for selling and removing expired batches.
Okay, so what happens if two products have the same product ID? How does your program handle that case?
So product IDs are defined to be unique keys in our binary search tree. So before inserting a new product, we always search the BST for that ID. If it already exists, the program does not create a duplicate node. Instead, it can add a new batch to the existing products queue. This prevents data duplication and keeps the BST consistent. Essentially, the system treats it as same product, new stock.
Okay, so in your show total product inventory function, why did you use in order traversal to display product?
So we use in order transfers because it is naturally display the nodes of a binary search tree in a sorted order. Here that means products are listed by ascending product ID, and this gives us a clean and organized output where items appear in a ascending order of ID and make it easier for the user to read and search visually. It also reflects how inventory lists are usually presented and in sorted predictable order rather than random.
Okay, so suppose you have two batches of same product that have same identical expiry dates. How will you handle such a case? Will you treat them as separate batches or will you merge them?
That's a good question. In our design, batches with the same expiry date, they are treated as separate entities in the queue, but logically they do represent the same expiry group. This keeps the structure simple. On each arrival of stock, even if it has the same expiry, it will have its own batch node in the queue. So an enhancement could be that we could merge them by adding their quantities together when the expiry date matches. So our current version prioritizes clarity over simplicity, but it's flexible for future improvements.
Okay, so our final question is that why did you choose to use a separate queue structure inside each product node? instead of storing all batches together in a single list or array?
So we have used a separate queue for each product because batches belong specifically to one product. Mixing all batches in a single global list would make the searching and updating much slower. With a per product queue, we only deal with the batches of products, that is, the operations like selling, adding stock, and removing expired items stay efficient and localized. It also keeps the program modular. If one product is deleted from BSD, its entire batch queue gets deleted too, which maintains the clean memory management. So, this design improves both performance and clarity of the system.
Okay, we are done with our questions. Thank you.
Thank you.
Hello everyone, I am Astha Singh.
And I'm Rakshak Shetty.
We are here to present our project, Hospital Bed Allocation System, a linked list approach. This project was developed for our data structures internal assessment, and it focuses on building a smart, dynamic system to manage hospital beds, especially for the real-time patient admissions and discharges.
In hospitals, manual or outdated bed allocation systems often causes delays, confusions, and errors, especially during emergencies when ICU beds are urgently needed.
Our goal was to design a computerized and dynamic system that automatically availability across ICU, general, and private wards, ensuring fast and efficient admissions, discharges, and real-time updates of hospital occupancy.
We choose the linked list as our core data structure because hospital occupancy changes constantly. New patients are admitted and existing ones are discharged frequently.
A linked list allows dynamic sizing, so we can easily add or remove beds without wasting money. It also handles frequent insertions and deletions efficiently, which fits perfectly with hospital operations.
And to keep things organized, we use separate linked lists for each ward. One for ICU, one for general, and one for private ward, making it easy to manage each category of the beds independently.
Now coming to the implementation details. So the core of our program is the struct bed node, which represents a single hospital bed. Each node stores bed number, patient ID, name and disease, and, and an occupied flag. So it is 1 if the bed is occupied and 0 if it's free. There's also a pointer next that links to the next bed in the same ward.
We start by initializing 5 beds in each ward using the create bed function. This function dynamically builds a linked list of 5 nodes where initially all beds are marked as free, that is occupied is equal to 0. So before any patients are admitted, our program has 3 linked lists representing the ICU, general, and private wards.
Coming to the implementation details. Patient admission. So the admission function is responsible for assigning a bed to a new patient. It begins by taking the patient's details such as ID, name, and disease, along with the ward name like ICU or general.
Then the function traverses the linked list of that ward using a pointer. For each node, it checks if the bed is free, that is, if the occupied is equal to 0. As soon as it finds the first available bed, it updates the occupied flag to 1. Then it stores the patient's data in that node and immediately exits the function.
This ensures that the first available bed is always given to the next patient, maintaining fairness and efficiency. If no free bed is found by the end of the list, the function displays the message, no free beds available in this ward.
So the system handles both successfully admissions and full ward conditions smoothly without any crashes or delays.
Coming to patient discharge. Now, this is used when a patient leaves the hospital. So it takes the patient's ID as input and then traverses a ward's linked list to locate that specific ID.
Once the patient's node is found, the function resets all the fields. It sets the occupied to the 0, clears the patient's name and disease information and marks the bed as free and ready for the next patient.
If the program reaches the end of the list without finding that ID, it prints no such patient with the given ID.
This logic ensures that the invalid discharges are caught and that no data corruption occurs. Overall, both admission and discharges operation are quick, efficient, and reflect changes in the real time.
Now coming to the reporting functions, starting with watch status. Now we also designed two important reporting functions, that is watch status and free beds for better monitoring.
The watch status function displays the status of every bed in a specific ward. It takes the ward's linked list head pointer and goes through each node one by one. If a bed is occupied, it prints the patient's detail, ID, name, and disease. If it is not, it simply shows bed X is free.
On the other hand, the free beds function checks all the three wards, ICU, general, and private, and lists only the unoccupied beds in each. This gives hospital staff a quick overview of which beds are free without needing to search manually.
Together, these functions make system transparent and user-friendly, helping administrators instantly know the availability across the entire hospital.
Now, coming to test cases. We tested the system under multiple conditions, which is normal case, edge case, and failure case. The normal case is a smooth admission and discharge of patients. Edge case is when the ward is full and the system correctly reports no free beds available. And failure case is when invalid patient ID is given during discharge and the system prints no such patient found.
All the tests are executed successfully, proving that system is robust, error handling capable, and works exactly as expected.
Coming to result analysis, our results showed that the system accurately tracks real-time bed status and handles frequent updates efficiently. It meets all the design goals, that is fast admission, safe discharge, and clear bed reporting.
The linked list structure was ideal for this use case. It provided dynamic memory management, reduced unnecessary complexity, and ensured smooth handling of the edge cases without any crashes.
Let's come to the conclusion part. In conclusion, a hospital bed allocation system demonstrates how a simple data structure like a linked list can efficiently solve a real-world healthcare problem.
It's scalable, reliable, and can be extended in the future. For example, by integrating it with a hospital database or a graphical user interface. So thank you everyone for listening to our presentation. We are now ready for your questions.
Yes. Your first question is, your system uses three separate linked lists, one for ICU, one for general, and one for private ward. What would be the advantages or disadvantages of combining them into a single list with a ward type field instead?
Okay, so our system uses three separate lists, which has their own clear advantages. So that the main benefit of it is efficiency and simplicity. When admitting a patient to general ward, the system only has to search the short general list. This drastically reduces the number of checks required, making the add patient function run faster. It also makes the code look cleaner and readable. The disadvantage of using a single linked list is that if we combine them into one long list, searching for one available bed in the private ward might require traversing through all the ICU and general beds. This increases the traversal time and slows down the allocation process for wards later in the list. Thus, choosing a separate list becomes very faster for core operation and simplifies the management of individual wards.
So your next question is, the patient name and disease fields use scanf, that is %s, which only reads single words. What modifications would be needed to accept multi-word inputs for patient and disease name?
Okay, so the current program uses scanf, that is %s. Now it is designed to read only a single word. To accept multi-word inputs, like for example, Astha space Singh or type space 2 space diabetes, we need to switch the input function. So the necessary change is that we must replace scanf percentage s with fgets in the add patients function. Fgets reads the entire line of text, including spaces. And the required cleanup is that because fgets includes the new line character /n in the string, we have to add a simple line of code to find and remove that new line before saving the data to the node. This ensures clean storage and prevents formatting issues in the output.
In your program, when a patient is discharged, you just mark the bed as a free instead of deleting. Why did you choose that method?
So in our system, each node represents a bed, not a patient. So when a patient is discharged, we simply mark the bed as free by setting the value of occupied to 0 instead of deleting the node. Technically, deleting a node would require additional pointer manipulation and memory allocation using free function, followed by reallocation with malloc, which is very inefficient. Keeping the node intact maintains the structural stability, minimizes the memory overhead, and allows faster use of reuse of beds.
If you wanted to prioritize ICU patients based on severity, how would you modify your data structure or admission logic to support priority-based allocation?
So if we wanted to prioritize ICU patients based on severity, we can enhance our existing linked list by adding an extra field in the struct bed, such as int severity, to rate each patient's condition on a scale of 1 to 5. We can also add a separate function that displays ICU patients in descending order of severity. This ensures that patients with higher severity are shown first, helping staff identify critical cases quickly. The main benefit of this approach is that it allows the medical staff to make faster and more informed decisions regarding treatment priorities, ensuring that the most critical patients receive immediate attention and resources, which can improve patient outcomes and optimize the ICU efficiency.
If you were to extend the system to make it more useful for the hospital staff, what additional features would you consider adding?
Okay, so expand the system and make it truly useful for hospital staff, we can implement various features that enhances the logistic and information retrieval. We can implement a field which is called as is_underscore clean to the node so that when a patient is discharged, the bed status changes to needs cleaning. Therefore, the add patient function would then only assign a bed that is both free and clean. We can also implement a transfer function to seamlessly transfer a patient from one ward, example IC ward, to another ward without requiring a full discharge or readmission cycle. We can also implement a search function which allows us to search by using the name or disease instead of just using the specific ID. This is much faster and more practical for day-to-day use. Do you have any more questions?
No, that's all. Thank you.
Thank you.